Hello and welcome to the DJI Zenmuse L1 Surveying course. This section introduces the key information needed to classify and clean your point cloud data in TerraSolid. It will show you how to export your raw LiDAR data from DJI Terra into TerraSolid. Finally, a step-by-step guide for the Process and Wizard will be used to classify your point cloud before using the Output Control Report tool to compare the point cloud to the true coordinates. The first step requires installation of the TerraSolid UAV bundle onto your PC. Type in TerraSolid UAV bundle onto your browser and click on the link that says UAV Trial TerraSolid. Firstly, ensure that the PC is the same PC that was used to previously install the DJI Terra software. TerraSolid will automatically recognise the activated license on this account, and as such data classification can begin straight away. However, before processing, the correct package needs to be downloaded and stored in the same drive as DJI Terra. TerraSolid provides two UAV bundles on the TerraSolid website. For those who have an existing Bentley account, the Bentley TerraSolid package will be the correct version for you. Simply ensure that the Bentley platform is already installed on the PC prior to installing the software. For those who don't have a Bentley license, the Spatix platform can be downloaded free of charge. Spatix is a small 3D CAD system developed by GISware Integro and provides the same functionality for those users who do not have an existing MicroStation account. To access the complete range of TerraSolid tools, a MicroStation license will be required. However, for the typical L1 user, the Spatix platform will provide everything you need. For the duration of this module, data processing will use the Spatix UAV bundle. Click on the link that says UAV Evaluation with Spatix Download, and this should take you to the next screen where you can add the item to your cart. As you can see, there is TerraScan UAV and TerraModeler UAV, both included in the TerraSolid bundle. TerraScan is the main platform used for managing and processing all types of point clouds, whereas TerraModeler allows you to utilize, edit and create surface models from various sources, including the LES and binary files that are loaded into TerraScan. Ensure you download the latest version of Spatix. At the time this course was made, this was version 021.039. However, newer options may be available as you come to download the software. Once you have added this order to the cart, select Proceed to Download, and you'll need to fill in your contact details and personal information on the TerraSolid website. Shortly after submitting your contact details, the TerraSolid team will send an email to your inbox allowing you to finish downloading the software. Firstly, if the TerraScan window has not loaded automatically, you need to activate the display by going to Application, TerraScan and then Main Window. In the TerraScan window there are a variety of features available, however for now we will just be using the wizard on the far right side of the display. Click on the wizard and then Start New Drone Project to start the TerraSolid processing. Firstly, the scanner system needs to be specified as the DJI Zenmuse L1. Below this we need to name our drone project. We are just going to call this Zenmuse L1 Surveying course. However, for your work I would recommend calling this after the name of your project. In the laser input box we need to locate the LAS file that was processed using DJI Terra. The output LAS file should be named Cloud, with a series of random numbers and letters after it. TerraSolid should automatically recognise the coordinate system, but if not we need to specify this as 4326 WGS84 latitude and longitude, and have the input elevation set as ellipsoidal. In your trajectory input we need to load in the spec.out file DJI Terra has created, which provides the raw trajectory data from the drone. Again, have the input system set to WGS84 and the input elevation set to ellipsoidal. The target system specifies the projection system where we want to work. Under the specified target system comes the target elevations. This can be specified as either ellipsoidal or orthometric. Ellipsoidal elevations represent the distance from a point on the Earth's surface to the ellipsoid, whereas orthometric elevations represent the distance from a point on the Earth's surface to the geoid. Some coordinate systems may require a geoid model to be imported. If the geoid model for your target system is not readily available in TerraSolid, you can download the geoid model online, and then select Points from File to import your model. Finally, in Browse, select to store your data in the same directory as your DJI Terra data. This just keeps all your post-processing outputs nicely organised in one place. Click OK and the software will read the point cloud in, transform the coordinates, assign colour to the black points, and import the trajectory information. If your dataset was particularly large and Terra has exported more than one LAS file for your dataset, simply rerun the Start New Drone Project window to load more LAS files into your SPATIX project. Providing that the trajectory information is correct, the point cloud should align automatically if you have exported more than one LAS file from DJI Terra. It is good practice to save your LAS files in its raw format before starting the data processing. Therefore, each time you begin SPATIX, you do not have to create a new drone project. To do this, click on File in the TerraScan display, Save Points As, and save your file as an LAS file in its raw format. We have saved our data as an LAS file in format version 1.4. We are calling our file Zenmuse L1 Surveying Course RAW. It's always good to name this as a RAW file as it's a good point of reference to have once you have completed your processing. Now the next time you want to upload your data, go to Read Points As and then import this dataset into the main window. TerraScan is the application for managing and processing your point cloud. The main toolbar you can see on screen now will be used for the majority of the operations in this module. Under View, there is the Displayed Mode icon which can be used to change the display of the point cloud. This can be used to display the point cloud either by point class, RGB colour or elevation. If you cannot see the point cloud clearly or it is not visible at all, you can use the Fit button to fit the point cloud to view. Certain classes can also be turned off and allocated to particular views. For example, once the ground layer has been established, all of the classes in the dataset can be turned off so all we view is the ground data. There is also the Show Statistics tool. Once you have finished your classification, the Show Statistics tool can be used to check how many points have been assigned to each point class. At the moment, all of our data is still in the default class, as the data is still in its raw form. The Processing Wizard was used previously to create the new drone project. However, it's also used for data classification and removing noise from the dataset. The Processing Wizard is the tool we will use to automate our processing. To view what class each point has been assigned to, we can select View Statistics to provide a breakdown of the point classification. On the left-hand side of the display, there are also a variety of TerraScan tools that can be used in the point classification process. Probably the most important tool throughout this module is the vertical cross-section. To choose the correct tool, simply click and hold on one of the icons on the left, and move your mouse down to select the utensil you need. The vertical cross-section is useful for verifying the distance between the highest and lowest point of the point cloud, or viewing how well the L1 has penetrated the vegetating canopy. Ideally, the vertical cross-section would be opened in a new view window, so you can use the top-down view in the existing window to understand your location in the point cloud. If you want to get back to the top-down overhead view of the dataset, use the horizontal cross-section tool and draw it over the vertical cross-section you just created. It requires 3 left clicks of the mouse, 2 to draw the area, and a final click to bring the cross-section to view. TerraSolid also provides a variety of ways to manually classify your point data. These are Assign to Point Class, Classify using Brush, Classify Fence, Classify Above Line, Classify Below Line, and Classify Close to Line. Using these tools, you are able to classify from one point class to another. We will look to manually classify some of the data later in the module using a DTM output from Terra Modeler. The final tool worth introducing at this stage is the View tool. To introduce new views into your document, click New View Mono followed by Window Tile. There are many more tools that can be used with the TerraSolid UAV bundle. This course aims to introduce the key concepts. Just to provide an insight into what else can be done, people who are in the rail engineering sector can use L1 TerraSolid data to classify rail tracks, electrical wires and gantries from the point cloud. MicroStation users can vectorize the building layer, so CAD drawings of the buildings extrude from the ground layer. Finally, for those concerned with volumetrics, the Compute Quantity tool can be used to calculate the cut and fill volume between 2 surfaces in an area specified using the Fence or Selected Shape tool. Next, we will begin data processing using the TerraScan Wizard. The TerraSolid Wizard is the interface used for classifying your point cloud data exported from DJI Terra. At the end of this section, you should have a fully classified point cloud removed of noise that can be exported to a DTM surface. Before we utilise the wizard to classify the dataset, it is good practice to manually remove noise from the point cloud using the vertical cross-section tool. If we draw a vertical cross-section around the entire dataset and assign it to view 2, we should be able to spot any anomalies that are present in the dataset. At the bottom of our dataset, we can see a few low points that do not align with the elevations in the rest of the dataset. I manually added these as custom synthetic points, so yours may look slightly different. That's if there are any anomalies at all. If we go to classify below line, we can then classify these as low points. From here we go to points, delete by point class, and delete all low points in the dataset. The first part of the processing procedure involves splitting the trajectories into the individual passes over the survey area. It is worth noting multiple tools can be run at once when using the wizard. However, for the purposes of this course, we are going to do it step by step so you understand the work of each function. In a processing wizard, we need to turn off all of the other processing steps apart from the split trajectories function. The settings can be left as default. Once we have pressed OK, the processing should complete relatively quickly, as the software is pulling the trajectory information from the sbet.out file we imported previously. Now we go to Manage Trajectories, Tools, and then Draw to Design. Before doing this, it is also worth increasing the width of the line to make the flight lines more visible. When creating the design file, make sure that is coloured by the trajectory number. The design file we created can be closed, and the flight lines can be viewed in the point cloud by going to Display Mode and then changing the view to Line. As you can see, the point cloud is now split into the colours of each flight pass, so we can see how much overlap there is between each line. Using the vertical cross-section tool, we can also verify there are no mismatches between the flight passes. Open up a new view window and draw the vertical cross-section to that view. Make sure the depth of the vertical cross-section is 0.1 meters. As we can see, there are no height mismatches in the data, however there is a lot of noise in the dataset. This is because the LiDAR unit was set to 50% overlap, so we will need to remove this overlap at the next stage of processing. If it is not doing so already, using the Display Mode tool, confirm that the new view is being displayed by line. DJI Terra has done the matching for us, and we are using the Spatics platform to verify how well the individual flight passes align with each other. Some passes may exhibit more point-to-point noise than others. The next step of the processing wizard uses the Cut Overlap tool. This keeps only one flight pass at each location, removes the edges of the scan corridor, and removes some of the noise present in the dataset. As can be seen in the vertical cross-section view, the software only keeps the better matching data, making the point cloud look a whole lot cleaner. Our data is now much more accurate than before. As we can see from the total number of points on the TerraScan window at the top, over half the data has been removed from the dataset. Step 3 will smoothen and remove noise. Click on the settings to check the parameters before processing. They can be left as default. As you can see, there is a non-vegetation only feature enabled. This tells the software to modify only the XYZ positions of the points that are not marked as green in RGB colour. The software recognises these features as an area of vegetation, and it would be wrong to disable the non-vegetation only function, as these points will be removed from the dataset, where in actual fact these features are a part of the natural land. For instance, they may be leaves as part of the tree canopy. We now click OK and the software will determine which points can be classed as noise and removed. Once the software has detected the noisy data, we can now remove these points if we go to Points, Delete by Point class, and delete all noise. However, we're going to leave the noise in the noise class for now, as we will look to assign some of this data to a point class later in the processing. If you wish to view the entire dataset as noise, using the existing view window, the display mode can be set to class. We can see from our dataset that a lot of noise is located near the tree line to the right and along the road. On closer inspection of the data when using the vertical cross section, there are a lot of points both above the line and below the line that have been correctly identified as noise by the software. We will now look to classify the ground layer. Classifying the ground layer is an essential step to later creating our DTM. Thinning the dataset is optional and assigns thin points to an inactive class. Essentially, it is used to speed up the ground classification and tells the software to not use all the points in the classification, but only a subset of the points that are active in the dataset. It can be disabled, however this will just increase the processing time. The settings can be left as default for assigning the thin points. The classify ground settings can be left as default, however for our survey we are going to change this to a 40 meter spacing. We now press OK. Once this has been processed, you could go into show statistics to understand how many points have been sent to the inactive class and how many points have been classified to ground. At this point here we'll have our first engagement with Terra Modeler and create our triangulated surface model. The purpose of introducing a surface model into our workflow is to evaluate how well the software has classified the ground layer. If we refer back to the wizard, we can see there is a check ground layer function. For this step we are manually checking the ground using a digital terrain model and removing any features that look peculiar. To create our surface model we need to click the icon that says Create Editable Model. Make sure the model is only using the ground layer. From here we can then go to Applications, Terra Modeler and Display Shaded Surface. The settings can be left as default and assigned to a view window to display the model. If the surface model does not show right away, we can edit the display mode in one of the views. For instance, in our document if we go to View 3 and select View by Class, we can then deselect all of the active classes which should display the DTM. If the model still doesn't show, we may have to fit the model to view. We can now scan over this model and classify any points that don't represent the ground layer. I'd recommend having an RGB point cloud opened up in a separate view so we can see what we are looking at on the shaded surface. We are going to open up a new view window and within the display mode set this to colour. For this, we will need to synchronise our view windows 2 and 4, so as we scan over the DTM, the colour view will show the same location. Generally, the surface model looks relatively clean as we scan over it. However, we can see there are some areas that look a little peculiar towards the centre of the dataset, so these need to be removed. I'm going to draw a vertical cross section around these features. Make sure that the vertical cross section view window is only displaying the ground point class. I can clearly see this should be a part of a building roof if I look at the RGB dataset, so I'm going to manually classify this feature above the line as a roof structure. This immediately cleans up the DTM. However, there is another part just off the building roof that I am unable to verify from the RGB point cloud. So using the DJI Terra 2D ortho photo, I'm going to zoom into this section of the image to work out what this land feature is. Looking at this feature now, it looks like an area of debris just off the farmhouse. I can't find a point class for loose debris, so I'm just going to set this bit of data as unclassified. Ultimately, I could check every little section of the dataset and manually classify points for the next couple of hours. However, at this stage, I am happy with the classification process performed by TerraSolid, and I'm confident that I have amended all the points that need to be reclassified from the ground layer. We have just completed the check ground step with the support of our DTM. In the final part of this section, we can return to the Processing Wizard and classify the above ground features and the height from the ground. We also want to copy our results back to the inactive points and noise points, as we no longer require a thin dataset. This ensures most of the points in the dataset are assigned to a point class. Firstly, ensure that the view windows 2 and 4 are unsynchronized, as we no longer require this function. We also need to close down our DTM surface as we have completed the ground classification. To do this, go to Application, Terra Modeler, and then Close Surface. The DTM could also be exported like it is now. Usually, we would export this as an XYZ text file and recreate the tin in another software such as ArcGIS Pro or QGIS. However, for now we are just going to close the surface, so make sure any changes made have been saved before closing the file. Returning back to the Geoprocessing Wizard, in the settings for above ground features, confirm that the vegetation index is selected so the software can deduce the areas covered with vegetation. These areas will be treated differently to the hard detail point classes. Check that you're happy with all of the other settings, but for our survey, we are just going to leave these on default. Once you've pressed OK and the processing is finished, we now need to check the classified above ground features to confirm that the points have been assigned to the correct point class. Firstly, we need to check the ground layer, so in view 2 we will have all layers turned on in the display and the display mode set to class, whereas in view 4 we will have the RGB colour point cloud. The vertical cross section will be used in view 3 to check the classification. We are going to draw a vertical cross section across the survey area and set the display to just a ground point class for now. The image on the screen shows that all the points accurately represent the ground surface. Next up, we need to check the building classifications, so in the display mode select the roof structure as class. The vertical cross section shows that the building roof has also been classified correctly, as the roof outlines are clear and visible. Finally, I'm going to check the tree class. You may have to increase the depth of the vertical cross section to a depth of 1 meter, so that the trees are more distinguishable in the cross section view. But considering what I can see here, I'm happy with how this has been classified too, as I can clearly see from each of the view windows what part of the dataset has been classified as a tree. It's entirely up to you whether you want to check more of the point classes. Ultimately, it depends on the features in your survey area, so if your project took place in a car park, it would be worth checking the point classification of cars. This concludes our use of the Geoprocessing Wizard for cleaning and classifying our point cloud. As you can see, the process is mostly automatic. It's just a case of checking the data every so often to confirm that the software has correctly classified each point class. Make sure the edits we have done are saved to a new LAS file before closing the document by going to File, Save Points As. We're going to call ours something like L1 classified and save it to the same folder as our DJI Terra data. The next module will look at validating the accuracy of our point cloud using the control points we marked out in the field. Using the data we collected with the GNSS receiver, we compare the elevation of our point cloud to the true coordinates. Firstly, we need to ensure that the control points are stored in an XYZ format. The MLID Reach RS2 was used to collect the data for this course, so the GCP positions are directly exported from the iPad to the computer as a CSV file. Firstly, ensure that you have created a folder for your GCP documents in the same directory as your classified LAS files and your processed DJI Terra data. In this folder, we have saved the CSV file directly exported from the iPad. To view the survey data, we are going to use Microsoft Excel. However, a standard Notepad document can also be used. The columns need to be arranged so they only show the easting, northing and elevation columns, in that order. All of the other columns in the document can be removed. This is the standard XYZ file format, and even though this will be saved as a CSV file, TerraSolid reads this as positional data. Once the document has been saved, it is ready for upload to Spatix. We also need to save our file as a tab-delimited text file. This is because we first want to load our data in as a design file and visually compare how well the point cloud matches the control points. Save the folder with a slightly different name to the CSV file, and then search for a tab-delimited text file from the list of drop-downs. To successfully load this file into TerraSolid, we need to reduce the spacing between the easting, northing and elevation to one click of the Space tab. So open up the recently saved folder and edit the file so it looks like the document on the video. Once you have saved your edits to this document, we can load this data into TerraSolid. We need to close the classified point cloud from before so it says there are 0 points in TerraScan, and then load in the recently saved text file. We go to File, Read Points and navigate to the GCP folder where we saved our files. Make sure that when you are searching for the files that you specify you are looking for all files, not just LAS files. When you load in the files, just check to confirm that the format is set to XYZ. Once the document has loaded in, the point should automatically show on screen. I want to make these points more visible in comparison to the point cloud, so I'm going to change the strength of the line to 5 and change the colour to yellow. Then we need to go to Output, Write to Design File. It's important that the class is set to active symbology in the design file so the appearance of the points change. Click OK and the points should change size and colour as we can see on screen now. We can now close the points from the TerraScan window as they are no longer needed. We are now going to read the points we processed before using the Geoprocessing Wizard. Once these have loaded in, we can visually compare the east and north components of the true coordinates to the point cloud. Firstly, we need to change the point cloud from class to colour to make the control points more visible. We now need to closely inspect each checkpoint to confirm that the point cloud is accurate in east and north direction. I'm happy with how the point cloud matches the checkpoints, as I can clearly see that the control points fall in the boundary of the GCP markers we used out in the field. We can also use the vertical cross-section tool to visually compare how the points match in elevation. If we draw a vertical cross-section around checkpoint 5 here, we can see that there is a slight difference in height, but nothing too serious. I would like to quantify this data and accurately know the difference in elevation, so for this we will need to use the Output Control Report tool. Using the TerraScan window, go to Tools and then Output Control Report. We're going to compare by elevation to verify the positional accuracy of the height coordinate. You could also compare the point cloud against the XYZ data, however I find this method less effective as it involves importing a signal marker into the dataset, and the results are not as informative as the elevation output control report. Ensure that the ground control is compared to only the ground class and a low vegetation layer. Finally, where it says Browse, load in the CSV file from before with all the control points. Once all the settings look as they do now, click OK and the software should start calculating. When TerraSolid has finished calculating the results, we can identify each checkpoint in the point cloud by clicking on them in the output control report. Overall, I'm generally happy with the errors for each control point. As for the average elevation difference calculated by TerraSolid, this is presented in terms of absolute error, so only the positive values of all the differences are used to establish the average error across the dataset. We can now see on the screen that the elevation error has an average magnitude of 0.0434 meters. This is a 43mm error, which is 7mm less than the spec of the L1 sensor quoted by DJI. I'm confident that the data is accurate and therefore valid. If there is a systematic error across all your results, the software can automatically compute an elevation shift to the point cloud by going to Apply and then Elevation Shift. This finalises all of the processing for the L1 course. I hope you have found the content helpful. The features explained in this module only provide an introduction to some of the main features in TerraSolid. If you want to extend on what we have done so far, there are a variety of other tools that can be used on your dataset. The outputs generated from this course can also be exported to other mapping softwares such as ArcGIS Pro or LSS for further data manipulation.